So I am Jake. I work at Google. I work on the Android team, and specifically about 18 months ago, Android actually announced Kotlin as a new supported language for the platform, which is why I'm there working on it. But a lot of this talk will be framed in the sense of, well, I'm going to introduce you to Kotlin. A lot of the talk will be framed contrasting it to Java and why the language exists. But really, the premise of this talk is actually about running Kotlin beyond just where it was originally designed to run. And so there's this effort called Kotlin multiplatform, which is what this talk is about. And it's taking this language that was built for a very specific purpose and the realization that actually it can run on more than one platform. And there's this sentence that comes from Java, which is the write once, run everywhere. And Kotlin is kind of taking that and delivering it in a different way, where it's not just the JVM runs everywhere and your Java code then runs everywhere the JVM runs. Kotlin is instead taking this and saying your Kotlin code can run everywhere, but it can do it in a way that's much more intrinsic to each platform. So I'd like to start with introducing the language itself. How many people have seen Kotlin at all before? OK. So that's good. That means this won't be for naught. Kotlin is a language that was created by a company called JetBrains. JetBrains are primarily makers of IDEs, of tools. And all of these tools are mostly written in Java. The foundation of this suite of tools is called IntelliJ IDEA. And there's a community edition, which is open source. And it has about 3.5 million lines of Java code. And then and that's just the community edition. There's an ultimate edition, which is paid, which has a bunch of extra functionality. And then all these other icons are IDEs for other languages, which are built on the IntelliJ platform. So that same Java-based platform, they then build language support and refactoring tools and all this stuff for PHP, for C. And so JetBrains, they're very aware of the pain points of the Java programming language. This is a company that's intimately familiar with the language. 3.5 million lines just in the base platform, and then however many million built to customize all these other languages. And so they know Java well. And geez, at this point, 7 or 8 years ago, they started looking for ways, and the years ago context is really important. This is Java 7 or 8 years ago as well. And so they started looking at other languages to help improve their productivity in the tools that they built. They looked at, and so because this is JVM-based, they're limited to JVM-based languages. They looked at Groovy, they looked at Scala. And they just found that while these other languages had a lot of the things that they wanted, they also came with a lot of downsides, whether it's performance, overhead, just complexity of the language. And they made a choice that is pretty bold, which is they're going to invent this new language. It's going to be compatible with Java, but since none of the other ones that were out at the time were able to solve the use cases that they wanted in the way that they wanted, and because they were a large enough company to invest these resources, they decided to build this new language called Kotlin. And so I want to go over what the language looks like to just get you familiar with, and this will play an important, I'll try and touch back on this over and over throughout the rest of the talk as to why knowing what the language looks like is important. It looks like almost any modern language you would expect. Now, like I said, this comes from people that had worked mostly with Java, but they're aware of the other programming languages that were coming into existence over the course of about 7 to 5 years ago, which is when most of the language work was done. So we have here some properties which are defined. The very first keyword denotes whether something is read-only or read-write. So val is a value, which means it has a value set, and then it cannot change. It's a strongly typed language, so everything must have a type that's known at compile time. And then it has the concept of optionality elevated into the type system. If you're familiar with Java, this is one of the biggest pain points of the language. That you can try and solve with things like annotations and static analysis, or maybe the optional type, which eventually came out in Java 8. But by having optionality in the type system, you're now forced to do things like null checks before you can dereference something. Oftentimes, the type can be known, can be inferred from the context, whether in this case it's a literal, that's a string, or maybe you're just calling a method and that method has a defined return type, and so you can elide it from the definition. Now, because this was a language that was built from Java and needing to work with Java, it had to have a really strong interop story. Similar to how Scala can talk to Java compiled code, or Groovy can use Java compiled code, this language needed to do the same. They recognize certain patterns that are frequent in Java and quite verbose. One is the so-called bean pattern, where you have this getter and a setter for a property, and then there'd be like some private field that backed it. And when you view this from Kotlin, what it's going to do is automatically recognize that pattern and collapse them down into a single property. And so you get this much more terse representation of something that you can read from, and it would call the getter, or you write to, and it calls the setter. There's string interpolation, something Java doesn't have, to allow you to more easily create, mix and match string literals with variables. And then if you just want to print the toString of an object, you can just reference it like that. And what's cool about Kotlin is they not only decided to do Java interop in the way from Java to Kotlin, they wanted the opposite experience to be something that was also pleasant. And so if you use a language like Scala or like Groovy, it has really good interop with code that's written in Java. But sometimes when you're writing in Java and interacting with like a library that's written in Scala or Groovy, there's things that can look a little weird, and you kind of have to jump through some extra hoops because of how that more powerful language works, that it can't express the same thing in Java. But Kotlin wanted to try and avoid this wherever possible. And so if we do the opposite of what was on the last slide, we just define now a var property, which means it's both able to be read and written to. If you consume this from the Java side, it looks like that getter and setter, the standard bean format. And so you can call the getter, or you can call the setter. And actually, when you compile Kotlin, it compiles, if you're targeting the JVM, it compiles down to bytecode. And so even when you interact with this property through just Kotlin, it's actually going to compile down to calls to like a get method or a set method. I talked about the read-only or read-write. So if we define something that's a val and try to reassign its value, that's going to be a compile time error. Whereas if we have something that's a variable, we have the ability to change it. And the IDE, because JetBrains is a tools company, not only were they developing a language, but they also were able to develop the tooling alongside of it. And so in their IDEs, IntelliJ especially, IntelliJ IDEA, they can do a lot of things to highlight parts of the language to just make your code better. And so mutability is often a point of where bugs are introduced. And so they actually will underline references that are mutable to just call out that this is something where you need to pay extra special care because mutability is in play. Now, in order to reuse a lot of the things that were present on the JVM, they added something that's common in maybe C#, which is extension functions, the ability to hang additional functionality off of a type that you don't control. Now, this is not exactly the most useful of methods, but given any date, you can now call an isTuesday function on it, and it will determine whether or not, we'll run the body, and it will look at the call site as if it's a member function, but it's actually, you're not actually modifying the date class. If you do Java, this basically compiles to just a static method. And in Java, you write a lot of static utility methods because you don't have this functionality, and they're hard to discover. But by, again, having the IDE on Kotlin's side, now if you just have a date and you hit the dot, it will actually auto-complete these extension methods and then import them automatically for you. And again, going back to the two-way interoperability, if you want to call this from Java, it will actually show up as an extension method. If this is in a file called date.kt, which is the Kotlin extension, by default, the class name will be dateKT, which is kind of awkward. But you can actually control this and make it whatever you want. So if you want to name it dates or dateutils, you can have that idiomatic behavior from both languages. And then it's got features of modern languages that you would expect, things like lambdas. the ability to just pass code as data. Function references, so instead of having a lambda that contains code, if you already have a function that contains code that you want to pass, you can just refer to it using this syntax. Higher level functions, and this is both an extension function and a higher level function. So we're extending the functionality of list, and we're adding this filter method. This is actually a built-in method in the Kotlin standard library, but we could write it if we want to. And so now anywhere someone has a list, they can call our filter method, pass in a lambda, and then we can, in the body of the method, do the obvious thing with the for loop. And what's nice about how the higher order functions work is this is like how you would maybe naively call it at the call site, where you call the filter method, you open the parentheses because you're calling it as a function, and then you pass in a lambda as the first argument. This is a pattern that shows up a lot, where there's a lambda that takes that has a single argument. So here we're just always operating on the items in the list. And so what you can actually do is not specify an argument name and just use the implicit it. But then the pattern of a lambda being the last argument in a function call is something that's quite common. And so what Kotlin actually did is allow you to move that lambda outside of the parentheses, which looks a little weird. But then because the parentheses block is empty, you can actually eliminate that altogether and get this nicer filter syntax where you call it with just the lambda. It looks a little weird. If you haven't seen this before, this is your first time seeing the language. But again, being a language that's statically typed and having the IDE on your side, there's nothing that can be inferred incorrectly here. And then this still works if there are other arguments. So there's a overload of filter called filter2, which allows you to pass in the destination list that you want to filter your list into. And so you can see here we have the parentheses, and we're passing that list, but then that lambda still stays outside of the parentheses. There's a cool function. So in the JVM, you rely on its compiler, its runtime compilers, its just-in-time or maybe ahead-of-time compilers to do certain optimizations for you, like inlining. You have a function that's called over and over and over again in a very hot path. You rely on the JIT to recognize that and then inline it to the call site, so you don't have to be constantly packing and unpacking arguments and actually jumping to that separate piece of code. Kotlin actually allows you to do this at compile time. If you know something is going to be called either in a hot path, or the overhead of creating the arguments is a certain way where you want to eliminate that. And so for this filter, you might be wondering why would you ever inline this function? And that's because if you've done filtering in a language without higher level functions like this, such as Java before Java 8, you would have to create a new local property that's like an array list. You would have to write the for loop over the current things. You would call the if statement. Your predicate would be inside the if conditional, whether you wanted to keep an item or not, and then you would add it to the destination list. And now what this is doing is saying you can have the ergonomics of the higher order function where it's much more declarative and all you see at the filter site excuse me, all you see at the filter site is a lambda. But the way this works is that lambda has to live somewhere, and so there's usually an object created for that. And that object, if you're targeting the JVM, has a class associated with it. And by inlining this function, you actually eliminate the need to have a class generated for what the lambda implements, and then at runtime, that object implemented. And in the bytecode, you get what you otherwise would have written if you had done it manually. And so you lose the overhead of both the jumping to the call site, but also the overhead associated with the lambda. Something that's important for contexts like if you're running on Android, where things like performance, especially on the main thread, is very key. And then since this pattern of just having classes that carry data is somewhat common, it's essentially ubiquitous, I guess. There's actually a shorthand for, this is a terrible user because it's always named Jake. But if you wanted to take in a name, this is what you would write. And because the pattern of creating an object that's like a record type that just carries data is common, Kotlin allows you to collapse the property and the constructor argument into one definition, and then you can actually just drop the curly braces because they're no longer needed. If you use this, though, you might be a little surprised. Like, you want to create myself again, and I want to print that out. If, again, you're running on the JVM, and I promise I'm going to get to multi-platform stuff eventually, it'll do like the default Java thing where it just prints the memory address, which is useless, because you need to override toString. But instead of having to override toString or also the other stuff that Java forces you to do for value-based types, which is like equals and hash code if you want to use them in a map, you can actually just use a modifier on the class called data, which communicates to the compiler that, listen, this is just a dumb carrier of other references. And I want you to generate that boilerplate automatically for equals, hash code, toString. And now we get like a toString that's actually sane. Almost done with the language here. Another cool feature of these data classes is when you have multiple properties. Very frequently, you'll see these returned from a function. And then you need to access the component bits of that type. You need to pull out the name, you need to pull out the age, and then use them somewhere else. And so there's this feature called destructuring, which is in a couple other languages. You may have seen it in like Python, where you can actually just pull out the component types using parentheses. You don't need a separate reference for this. I mean, this is kind of stupid. I'm just creating an object and then destructuring it. Where you usually see this is when it's returned from a function. Function returns, a point, and you pull out x and y, or a user, and you pull out name and age. OK, 2 more language features before we move on. Something that this, again, is in the context of Android, but it applies to everything. We may have a property where it's expensive to initialize. And so in this case, I'm creating a property that actually talks to the database and creates a compiled statement, which is like, I'm going to execute this SQL query over and over again. So I want you to compile it to a more efficient representation. But the problem is this happens like eagerly. As soon as I create this class, the very first time I create this class, it goes and does I/O in the constructor instead of, say, the first time I call the delete method. And so there's patterns to avoid this. You can have like a lazy pattern where maybe it's nullable, and then you check if it's null and initialize it the first time. Kotlin has this concept called delegated properties, where you basically say, I have a certain behavior that I want to apply to a property. And it will, every time I call get on the property, it will call into this like delegate object that has certain behavior. And so one of the ones that's built in is a lazy delegate. And you give the lazy delegate a lambda. And what this does is, when you call get, it does the annoying lazy pattern where it checks if it's null. If it's not null, it takes a lock, calls the lambda, gets the return value, sets that to its field, and then returns that to you. And then the next time you call get, it checks its field. That's already non-null, and it just returns it to you over and over again. And so that lazy pattern, the pattern of lazy initialization, is something that you can repeat over and over and over again. But what property delegates allow you to do is encapsulate that behavior in a class and then delegate your property behavior to that class. And that class is actually, the lazy is a function that returns this property delegate class. And so that function then takes this lambda. And there's a bunch of these property delegates. Some of them are built in, and you can write ones yourself. So an example would be, maybe you have a side effect you want to do every time a property value changes. You want to log for debugging or for analytics purposes, whatever. You can have a lambda called back every time this property is changed. To the consumer, to the person consuming this name property, they're just reading and writing a string property. They don't see the delegate. But then you have this behavior attached to it automatically. Because nullability is a concept in the type system, sometimes a property will never be null, but the value isn't immediately accessible. Like, it has to be initialized just after an object is created. And so there's a delegate that basically allows a property to have a non-null type, but if you call get on it before someone has actually set a value, it'll throw an exception. And this is nice because then it doesn't force the consumer to always do that null check. It encapsulates it inside the property itself. And then you can write your own. So like I said, I work on Android. Android has this view system. And so you can write a delegate that will go out and bind a view given a certain ID to a certain type. And then you never know this. You just interact with the property, the name view, and it will lazily go out and find the view the first time you call it. And then last language feature, something that's really new, just became stable actually a week ago, is this concept called coroutines, which are a lot of times they're described as lightweight threads. And so this piece of code, it's actually an old piece of code. It's a really old example they like to show, JetBrains likes to show, where they launch 100,000 coroutines that all sleep for 1 second and then print a dot. And so if you try and do this with threads, launch 100,000 threads, like that's not going to work. You're going to get it out of memory, especially if you do this on the JVM. But with coroutines, this really just creates 100,000 objects, and then there's a single thread with a looper that basically is just waiting 1 second until all these delays are up, and then it just runs through the 100,000 objects and calls the print method. And so this is actually only one thread, just 100,000 objects that are really lightweight compared to something like threads, which are very heavyweight. OK, that was just kind of a quick whirlwind tour of a bunch of features of the language. And I'm going to try and reference that over and over again of why Kotlin is something that started for the JVM and then moved outside of that space. And so when I think about something like multi-platform and running everywhere, the modern version of this, is really 3 platforms, which is native, which I'm representing with iOS, but this could be native running on like a microcontroller or your desktop or whatever. Then you have JVM Java bytecode, which I'm representing with Android, but it could just be running on your backend server. And then the web, which I'm representing just with a Chrome icon, but obviously all web browsers, or even potentially a JavaScript engine that's not a browser, Node.js, or maybe just an embedded JavaScript engine in another application. But really, it's the platform, the targeted platforms that are important: Java bytecode, JavaScript, and native. That gives you everywhere. And the important thing is, you can get everywhere with just native, right? Like native code can run everywhere. You can do native code on Android. You can do native code on desktop. You can do native code in the browser with WebAssembly. But these aren't inherently intrinsic to each of these platforms, right? If you write a native application for Android, it's very different than how a normal application is built with the managed bytecode and the SDK they provide. And for the browser, WebAssembly runs in certain contexts, but can't do stuff like interacting with the DOM, the actual JavaScript that traditionally we associate with the browser. And so Kotlin has a notion of platform independent and platform dependent Kotlin. And what it does is when we use Kotlin, traditionally we had been talking about Kotlin targeting the JVM, whether this was for backend servers, desktop applications, or Android. But over the last couple of years, JetBrains has come to realize, and if you think back to all the language features that I've walked through, there's nothing specific about the JVM in the language itself. It's just features of a modern language, features that we would expect of any language. And there's nothing that really prevents that from targeting a backend, a language like a compilation backend, different from Java bytecode. And so the JetBrains started with JavaScript about 2.5 years ago at this point, where you could compile platform independent Kotlin, which I'll talk more about what that means later on. You could compile that directly to JavaScript. And then over the last year and a half or so, they've targeted native as well. And so you can now compile this platform-independent Kotlin to native. But then there's also platform-dependent Kotlin. So like if I'm writing Kotlin for Android, I need to be able to reference Android types. And if I'm writing Kotlin for JavaScript, maybe I need to reference types from the DOM. Or if I'm writing code for native, I need to reference types from like libcurl or any native library that I'm interacting with. And so when you use Kotlin in a multi-platform context, the way that I've seen, the way that it's easy to get started with is to separate this out from the rest of your application, where you have, say, a library that is either business logic or just some encapsulated piece of code that you could then write in Kotlin, compile to each of these backends, and then consume it as a library. If this is Android or Java, consume it as just a jar. If it's JavaScript, you just consume it as through npm or whatever. You don't even need to know that it was written in Kotlin. And if it's native, you just consume essentially the header and then the compiled binary. And the rest of your app gets to be written in the thing you are already writing it in. C, C++, Go, Rust, Swift, JavaScript, TypeScript, or Java, Scala, Groovy, or even Kotlin, right, if you're targeting Java backend. But this is like a very easy way to introduce it into your app, but you don't have to do this. If you want to have Kotlin everywhere, you could have just your app be this whole multi-platform abstraction where the majority of it is Kotlin, and there's very specific parts that are platform specific. And I want to go through an example of what this actually would look like in order to motivate it a little bit more. I'm going to use a concrete example, which is a game. We're going to build a tiny little game, which is tic-tac-toe. And we're going to have it run on 4 platforms. Android through the Java backend, iOS through native backend, the web through the JavaScript backend, and then the server can be through any backend. Could be running Java and using the Java bytecode, could be Node.js pulling in JavaScript, or C, C++, Go, Rust, whatever, through the native backend. But I'm an Android developer, so the way that I usually teach Kotlin is by starting through Java and then working my way to the other platforms. And so if I've written this game, say I just have written the model here for representing the game, and I've written it in Java. So I have, whether something's an X or an O. I have the board, which is just a 2-dimensional array of the cells and whether they're marked or not. The player has a name and whether they've assigned the X or the O. You don't need to really pay attention to what's going on here. A state machine, these are the states of the state machine. It's either one of the 2 players moves, one of the 2 players have won, or it was a draw, nobody won. And then you have the game, which encapsulates all this, has the state machine, it has the 2 players, and the board. And so, I've been hammering on the Kotlin interop story between Kotlin and Java, and it's something JetBrains has certainly been talking about. And so we have these objects, and these objects are connected in a tiny little dependency graph. And maybe you just go and grab the player class and say, well, this looks like that. This is just a dumb carrier object of 2 properties. It's the name of the person and the name of the player and the whether they're an X or an O. I have to write this equals hashcode in toString, and I just talked about how these data classes allow you to create record-like types. This is a good candidate for turning into a Kotlin data class. And now I get to show my boss that I replaced 150 lines of Java boilerplate with just 1 line of code. And now I'm more efficient as a programmer. And but this is a little weird because what we've done is actually created a cyclic dependency between 2 languages. We have our mark class, which is written in Java, which was the X or O enum. We have our player class, which then has to hold on to a mark reference for each player. And then our game board has to hold on to 2 player instances. So we have Java referencing Kotlin and then Kotlin referencing back into Java. And this is one compilation unit. So all this code is going to be compiled in one module. This is our model. But this actually works even though it seems like it shouldn't. This cyclic thing shouldn't work. Because either the Kotlin compiler runs first, which compiles the Java bytecode, and then the Java compiler runs, which pulls in that Java bytecode as a library and compiles the Java, or the opposite has to happen. Java compiler runs and spits out Java bytecode, and then the Kotlin compiler runs and eats the Java bytecode and spits out more Java bytecode for the Kotlin. So it doesn't seem like this should work, but it does work. And this is one of, again, it's not even just about having the interoperability between the 2 languages. It's about making the toolchain work in a way that's conducive to you migrating to this language. Because otherwise, we don't need this language, right? There's enough languages. Every now and then a new language is invented, and it comes with a very specific purpose. But another language on the JVM, or at least that started on the JVM, doesn't seem like something we need. And so it's really important to have this really good interoperability story, both in the language, but also in the toolchain. The way this actually works is that the Kotlin compiler is both a Kotlin compiler and a Java compiler, except it doesn't actually compile the Java code the whole way. It goes 50% of the way just so that it can read enough to understand what will be compiled by the Java compiler. And so you feed both things, our 4 Java classes and our 1 Kotlin class, into the Kotlin compiler. It compiles only the Kotlin class using what it knows from the Java classes that will be compiled later. And then the Java compiler runs after the Kotlin compiler, and it takes in the class file, the Java bytecode class file of just the 1 Kotlin class, and then our other 4 Java classes get compiled again, except this time they get compiled the whole way. And so you spit out the 4 class files for Java code, and then the 2 bytecode outputs are combined. And that's how we get like this cyclic dependency to work. And then the standard library or any other libraries that you're using, any other Java libraries, are just available on both class paths. And because they are made available to any downstream consumer. And if you want, like this can be, like I said, this can all just be encapsulated in a module, and nobody downstream of you has to know you've written in Kotlin. So I've just been talking about this like hypothetical model of this game, and only for Android, I guess, for the Java backend. But if we take a step back and look at what all is required for building something, even as simple as just a tic-tac-toe game, where we actually want to host it and deploy it. We have our mobile clients where they're pretty much going to be the same thing, right? Like they're going to have view models that represent what's being displayed on screen. Maybe there's presenters which deal with talking to the network backend. And then with the web is a different client. It probably renders a little bit differently, at least a more sophisticated app would. But there's still backend infrastructure that you could share, which is like how you talk to the server. And then you have the server API, which then which interacts with the rest of this, where they all share this, the business logic, which is maybe like the state machine of the game, and then the models, which was what we were just talking about. And so we've really only done one thing here. We've just converted like the most basic part of our application to Kotlin. Can we do the rest, and how does that work? So if we look at just the mobile clients, the view models, these are also just dumb data carriers, so we can just write these in Kotlin. And then they'll, because they're platform independent, they don't, which again, unfortunately I only distinguish between platform independent and platform dependent a little more deeply at the end. But there's no references to like a platform here. We're not referencing iOS, like a UI view controller or an Android view or web, like anything in the DOM. These are just dumb objects, so they're trivially compiled to every platform. Presenter is also very similar, except a presenter has to talk to, say, persistence. So maybe like our games are being saved locally, and so we're going to take that in as a reference, and then we query like the game store for. So this is the like new game screen where we show how many games you've won. So maybe we query for the totals, and then we just return that dumb object. And then when you're actually in a game, like that takes in the ID of the game you're playing, the game store so that it can query the game information, using like a type called observable here, because the game state's going to update over time, and your UI has to update them when the game state changes. And observable is just a way to like push updates to a model, but nothing platform specific here. And then interactions from the UI come from here. And it really just, or if you like Redux, you've done the web stuff, you can have like states coming in and states going out, and you're just a state machine. But this is all just pure like Kotlin code again. And so it becomes really easy to see that each of these layers don't have anything specific. Maybe the web, like this is a super dumb example of tic-tac-toe. Like you could probably just reuse these models. A more complex product, you'd probably split these out. But the client backend is where things get a little more interesting. So I've just been talking about dumb records that carry data and pure Kotlin logic in the presenters. The game store that I reference is persistence, and persistence is something very specific to each platform. And now we can get into something where there's the difference between platform independent and platform dependent Kotlin. So we start with an interface. I didn't talk about this suspend keyword. That's another coroutines thing. It basically means the function is asynchronous. And so it can only be called in certain contexts, but you can think of it as like a a function that calls a function that has a callback under the hood, but you don't program like it has a callback. You program in this nice imperative flow. And that's because this is going to hit like a database or the file system in order to look up these like totals for displaying the overview. And then we have the current state of a particular game, and then the ability to actually like record a move, which we have to like call out to the server and like to ask it to play this move. Also a asynchronous operation. And so this is just an interface, but we need this logic of how this is actually implemented. And so the interface is just, again, boring Kotlin, but the implementations of that have to be platform specific. On Android, we want maybe a database. On iOS, core data. On the web, maybe like local storage. And so this is where we start getting into how we differentiate between platform specific and platform agnostic. Kotlin, and it doesn't look that different. So for the Android one, like this SQLite database type is a Android SDK. It's a type in the Android SDK, only available to Android platforms. And so what would have to happen is now we're writing code that's platform specific, and these would have to be in, it's not quite separate compilation units, but you sort of compile the same project multiple times and then mix and match which source files are contributing to it. And so the interface you could like have in a library, but then you start getting just tons of like modules for the only purposes is multi-platform. What you really want is just the interface and the implementation and sort of one representation of a module. And so the interface and this platform-specific implementation would be compiled by Kotlin C and Java C in one module. And then when we get to like iOS, it's still the same module, but it's a separate compilation. And so here we reference like core data, and I'm not showing the implementations because they don't really matter here. But you're talking to the actual native platform, and you're doing that from Kotlin. We're going to look at how you can do that from different languages in a second. So because Kotlin was built to start interacting with the JVM as its primary platform that it runs on, the interop there is very strong, and the way Java works is there's no real header files. You just kind of infer the headers from the jar itself. The jar, which has the Java bytecode, contains like a representation of what APIs you can call. Native, that's a little bit different, and so for something like calling into core data, you would need the headers that you're actually able to link against. And so the Kotlin Native compiler allows you to specify which headers you want to be made available as Kotlin API. And so we'll look at this a little bit more later, but it basically, you give it a header and it creates this almost like stubs in pure Kotlin that you can then interact with. So instead of having to, if you only know Kotlin and want to write something targeting native like iOS, you don't actually have to interact with something like Swift or Objective-C. You can allow Kotlin to synthesize stubs in the Kotlin language that you only interact with. And then JavaScript, we use like local storage. And what's interesting here is that Kotlin's standard library is something that also has a platform agnostic and platform specific versions. So there's APIs that you can call in that common code, like the interface or the code that's just like the view models. You have like a list, you have primitives like string and integers. But if you're compiling to a platform specific standard library, compiling against a platform specific standard library, you have types that are available in only JavaScript, like the DOM storage APIs. And so these are, they're again like stubs. They don't actually exist as implementations. When you compile this code to JavaScript, which we'll see in a couple more slides, it actually just it calls into the JavaScript APIs directly. And this is one mechanism that allows you to have both the platform agnostic client backend, which is the concept of storage, and then platform-specific implementations that are specific to Android, iOS, and the web. And then business logic is just boring. It's a bunch of just state machine code, which you don't need to look at. And that can be in Kotlin. And then everything becomes Kotlin multi-platform. And then all that's left, if we do this hypothetical thing and we go like full Kotlin or whatever, all that's left is the view part, the rendering part, which is platform specific. And so in Android, in Kotlin or Java, you could write Android's version of views. In iOS, this is Swift. So Kotlin types are made available in Swift and Objective-C. And so like this UI model, which came from the presenter that was written in Kotlin, you can use in Swift. JavaScript, because it's not typed, it doesn't really matter. You can just write the JavaScript as if the types are there. I believe it will generate TypeScript definitions from Kotlin. And in a second, I'll show a slide. It actually does the opposite. And then in like Java or whatever, this is like JAX-RS or whatever it's called for writing out a Java backend. So this is like a very pretty picture where you have all of your Kotlin code. You're using Kotlin because maybe you're just like this small shop or an individual developer, and you have the ability to target all three of these platforms where there's a lot of ways people can get into these platforms. That no matter how people get in, it's all the same code, and so you don't have to worry about the fact that like this person is using a Chromebook, and Chromebook has like installable Chrome apps that are just websites that you can install. Or Android has this thing called instant apps, which is maybe they visit a website and it just in time installs and launches an app. Or iOS is getting support, or macOS is getting support for native apps next year. And so your iOS app can now run on the desktop. And because it's all the same code, it doesn't matter how the user gets into your system. Like your business, like everything is just the same because it's all written in the same code base. Okay, I want to talk very, very quickly about how each of these implementations work. I talked about Java a lot. The Java is the thing that I know. The JVM and the Java C compilation is like the thing I know the best. So I already showed how that worked. For JavaScript, the way that APIs from JavaScript are generally exposed is through stubs that you can write yourself or that you can have generated automatically. So I work on something that's a Chrome extension written in Kotlin. And so I've defined Chrome's APIs using interfaces, stubs, with this external annotation, and then an implementation of that, which is like a property that is the root, that how you get to that object called Chrome. And like I've named it how you would name it in Kotlin, but then I can tell it how it's actually named in JavaScript. And now if there were TypeScript definitions for the Chrome APIs, which there might be, I haven't actually looked, there's a tool which can take any TypeScript definition and generate these stubs for you automatically. So if you're pulling in dependencies that have TypeScript definitions, you don't have to write any of this yourself. And what's nice is when this actually gets compiled, so this is a line of code from the Chrome extension where I'm creating an object and I'm passing in reference to Chrome storage. And I'm using the Kotlin uppercase C property reference. When this actually gets compiled to Kotlin, it looks like what you would have written if you wrote the JavaScript directly, which is the lowercase Chrome reference. And you see like the other code kind of got mangled a little bit because of how the Kotlin compiler represents stuff in JavaScript. But it spits out just pure JavaScript. It's like JavaScript that you would have written had you written it directly. It's not exactly idiomatic, but it's nice enough that you definitely could, if you wanted to, you could interact with it from other JavaScript or other TypeScript code. And then native, which is the most interesting one, this like emerging platform. It's the newest. Where I showed earlier about how we had the core data thing, and we pass in the headers. The way this actually works is you give it a package name, and it works similar to the TypeScript to Kotlin tool, where it's going to take in the headers, read them, and then turn them into like Kotlin-specific stubs in this package. And so here we would have an import, like if my GameStore.h had a core data GameStore type, it would be, I would just import that as if it was something in Kotlin, and I never really have to know that it was written in another language. The way that this compiler works is quite similar to how the Java compiler works, where the header files come in into the native compiler, which is called Conan. And then it spits out LLVM IR. And so this is how it essentially was free, not free because there's work being done, but the ability to target every platform that LLVM targets came for free. And so this is what gets you running on iOS, macOS, Windows, Linux, WebAssembly. And then LLVM takes in the headers as well, and it spits out the platform-specific machine code that can run on all those platforms. And so the hard work here is just translating Kotlin into LLVM IR, and then everything else, like all the optimizations and stuff, basically come for free. I'm skipping a section because I'm out of time. So I work on a project called SETI Search. It's a little side project just so that I can mess around with this kind of stuff. And it's an Android app and a Chrome extension. And so this pattern that I have implemented, or that I have talked about in the tic-tac-toe, you can kind of see here where the orange is like the Kotlin platform agnostic stuff. And then there's front ends for Android and for the web. And so the way this manifests is that now I essentially just write something once and it runs on Android. And then when you're in Chrome, it's a very different user interface, which is just the Omnibox in Chrome. And so very, very different front ends, but same exact back ends. And then for, I don't do iOS, it's an Android app, so I don't do iOS. But the Kotlin conference app that JetBrains hosts every year, they've written their app in this entire model where the Android and iOS apps share essentially all of their code. And so what I really wanted to convey here is that the language didn't start out as something that was intended to run everywhere, but because it's just a language that has been built with features that any modern language could have, and that it becomes then, I don't want to say easy, but it becomes almost obvious that targeting more than Java was something that was going to happen. And by doing only JavaScript and LLVM and everything it provides, you essentially get every platform. Java bytecode, JavaScript, and native means you're going to run everywhere, but also you run in a way that's intrinsic to the platform. You're not running native code in an Android app and having to do jumping through a bunch of hoops to interface, or even native code running on the web where you basically only have WebAssembly as your target, which is useful for certain things, but if you're doing visual stuff, the actual UI that the user interacts with, it's not the thing that you want to have, at least not yet. And so by targeting JavaScript, you get the ability to get the things that are intrinsic to that platform. So that's all I have. I have run a tiny bit over time, but I will be happy to stick around and answer any questions you guys have. Thank you.